have like a topic that you really like, you can go there and present. So I will be dropping the
Yes, it's recording.
information. I'll be dropping the information later in the chat. So you guys can join. And if you don't want to present, you just want to go and listen to people, that's cool too. I'll send the information later. And okay, so I think it's 5:05, so let's start very quickly. Welcome everybody. So today we're having our SPS Symposium. We're having three undergrad students presenting their research. We're going to be following this order. First is going to be Carlos Gonzales, and then we're going to have Nina Robbins, and last we're going to have Rafael Nunez. So yeah, if you guys can please introduce yourselves a little bit, say your name, your pronouns, your the short title of your research, and a cool fact about you. We can go with Carlos first.
Okay. Yeah. So I'm Carlos. My pronouns are he, him. So yeah, I'm a fourth year student. I'm doing research in like 2D materials in solid state physics. So yeah, I think it's pretty interesting for me. And I guess one interesting thing is I like to go on hikes and see the outdoors.
Thank you. Nina, can you tell us a little bit about yourself?
Hi everyone, I'm Nina. I'm also a fourth year undergrad and I'll be graduating in June. And I'm studying astrophysics at UCSC. And oh, sorry, I use pronouns she, her, forgot about that. And I've been doing research on modeling the thermal emission of hot Jupiters, which is what I'll be talking about today. And one interesting fact, I guess I'm originally from Spain. So yeah.
And Rafael, you go.
Hi, I'm Rafael. My pronouns are he, him, but I'm pretty fluid about them, so it doesn't really matter. I am a fourth year astrophysics major, like many people here. And I have a cool fact, I guess, is I like reptiles. I have a boa constrictor in my other room and a little plains or western hognose. I love them. Oh, and my research is on spectroscopy and time domain photometry of variables and transients. Cool.
That's really cool. I'm really excited to hear all of you talk about what you do because I haven't never heard, even if I've met you before, I've never heard what you do. So whenever you're ready, and I'm just going to make sure. Alberto, are you the host? Would you mind enabling screen sharing? Let's give him some time to do that. And in the meantime, so just to let you know, we're gonna have, so each presenter is gonna have 15 minutes to go over their talk. And if, of course, there's some space for you guys to ask questions and everything. And we're gonna have some extra 5 minutes at the end to ask questions and hang out. Let me double check with Alberto to see if he's still there because I'm not the host. Okay, so it's gonna take a little bit. He's on his way. So yeah, there you go. So we have a couple of questions from the chat. Someone is asking, Nina, which part of Spain are you from?
I'm from a town that's a little bit north of Barcelona, but I just say I'm from Barcelona because it's easier, but it's about 30 minutes away. It's a town by the beach. Pretty nice.
Nice.
What about you?
My mother is from southern Spain, like Cordoba and that area, Andalusia.
That's so beautiful.
I know, I
That's
love
really
it.
cool.
I was I went there a few years ago, and I went around. I stayed in Barcelona for like a week. It's really cool.
Nice.
Yeah.
Can I pipe in on you guys as well? My family are from San Celoni, which is a little like northeast of Barcelona as well. Yeah.
Okay, I was wondering when I saw your name because it's very Catalan.
Yeah, Bologna. Yeah, parles català.
Sí, clar.
Yeah, yeah, molt bé. Yeah, la meva és una mica yeah, my Catalan is a little shaky, but that's cool. I haven't met somebody from that region in a while, so.
Me neither.
Yeah.
That's awesome. Gotta practice our Catalan.
Yeah, for real.
Have you guys ever heard of the town Figueres? It's somewhere a little bit north of Barcelona. You've heard of it, Nina?
It's a beach
yeah.
town, right?
I honestly don't know, but I guess that's where Dalí was from, and he built a museum there, and it's really beautiful. But yeah, people like most people speak Catalan and like sort of barely speak Spanish there. It was kind of hard to get around, but it was so cool.
Yeah, a lot of people over there in Catalonia are very particular. They only want to speak Catalan because I think there's been a history of people wanting to take away the language. So they're very passionate about speaking it.
Definitely. Yeah. Yeah, I was gonna say I think they probably do speak Spanish. They just didn't want to.
Yeah.
Especially not broken Spanish to me. I tried to speak, like I don't speak fluently, and when I went, every time I was, especially in Barcelona, because everybody there speaks English. And when I would try to talk to them in Spanish, they would just like roll their eyes at me and just answer me in English.
Thank you all for that. That was really cool to learn more about her. My sister is in Madrid right now, so there you go. We all have like maybe less than 6 degrees of separation between each other. Okay, so I think screen sharing is enabled. Carlos, let me know if it works.
Yeah.
Okay, perfect. So go ahead.
All right. Does the slide appear?
Yeah, I can see. Thank you.
Okay. So today I'll be talking about the fabrication of two-dimensional twisted angle. Material is any material that is less than a few nanometers thick in one dimension. 2D materials exhibit different physical properties than their 3D counterparts. Recently, 2D magnets have started being studied extensively for their ability to alter the magnetic properties of a van der Waal heterostructure. And so here I have an image of a 2D heterostructure composed of 3 different 2D materials. So they're essentially just like paper just stacked on top of each other. So next up, what is a twisted angle? So a twisted angle is the term used to describe a heterostructure where the lattice structure of each material is offset within a few degrees. This was first studied with twisted bilayer graphene, and fascinating physics came out of it. And it was so interesting that it inspired researchers to attempt twisted heterostructures with different materials. So attempting twisted heterostructures with 2D magnets introduces the additional ingredient of magnetism that can lead to observing new phenomena that hasn't been discovered before. So here's an example of like a lattice structure. So this is like a honeycomb lattice. And so this would be a similar material where its lattice structure is offset by about 3 degrees. So if we bring them together, you can see that there are regions where the structures completely overlap. And this is known as a moire pattern. And this is what causes the interesting physics that that people want to discover. So next up, what is the edge alignment method? So this is essentially one of the first processes that was used to obtain a twisted angle heterostructure successfully. The method involves aligning the straight edges of a crystal with another that has the same degree edge. So these straight edges signify the rotation of the crystal's lattice structure. And ideally, the layers will be stacked to form a heterostructure where the lattice structure is aligned within a few degrees offset. So here I have an image of a chromium trihalide heterostructure that I created in the lab. And so here's another one. So I've highlighted the edges where the degrees are the same. So this is about a 60 degree edge. And so essentially what I would do is bring them together and align it so that these edges are on top of each other. So next up, why chromium trihalides? So chromium trihalides with their notation as CrX3, and this X can be either bromine, chlorine, or iodine within that halide family. So these have unique magnetic properties that can be proven to be a useful magnet. And chromium trihalides have shown to be magnetic insulators, and their properties actually get stronger as they get thinner. However, they do possess air sensitivity, and this can be a problem because the material starts to degrade when it's out of a controlled environment. And so here is an image of the structure of a chromium trihalide. So in blue is the chromium atoms together that form like a honeycomb lattice, and then the purple corresponds to the trihalides that are going around it in an octahedral frame. So for characterization of 2D materials, so this is how I perform. This is how I'm doing my research. So I exfoliate 2D flakes on 285 nanometer thick silicon dioxide substrate, and then I observe it under an optical microscope. So I use the Scotch tape method that's to exfoliate these thin flakes onto the substrate. And so the Scotch tape method is essentially just exfoliating the thin flakes out of bulk crystals. So I use atomic force microscopy, or AFM, to determine the thickness of chromium bromide flakes. And so because the target thickness is a single or bilayer chromium bromide, then using AFM is essential to know that these flakes are as thin as we need them to be. So chromium bromide is encapsulated between few layer graphene flakes to address the air degradation issue. So encapsulating the magnet between materials that aren't air sensitive keeps this material from being exposed to the ambient environment. So here I have an image of a graphene flake that is exfoliated in the lab. And so I utilize some software in order to be able to identify different characteristics of it. So the red line corresponds to the length of the flake. So so it's about 60 micrometers wide. And then the small blue and green lines correspond to the color contrast between the substrate and the graphene flake. And so because graphene has been studied extensively, we've been able to form a baseline. So we know that about like 9.5% will correspond to like a single layer graphene. So if we were to see something like 18%, then that would mean that it's a double layer graphene. So then here on the right is a chromium bromide sample. And so this is how it looks like under the optical microscope. So the thin chromium bromide sample is actually very hard to see under the naked eye. So it's within that circled region right there. So it's pretty difficult to see. You have to essentially train yourself in order to be able to identify this small contrast in the image. So here's an image of the same flake, and after scanning it under the AFM, it'll give me an image like this. And however, this isn't precise enough in order to be able to get an accurate thickness of the flake. So I would do a scan further zoomed in onto the actual flake that I'm looking at. And after doing a height retrace, you can see that the height difference between the substrate and the flake is about 8 angstrom, which is about 0.8 nanometers. So we know that this is within the region for a single layer chromium bromide. So what transfer method? So this is how I actually create these stacks. So I utilize what's called the PET pickup method. So I have the PET, which is a polymer, and I place it over the over the material that's exfoliated onto the substrate. So the PET is brought down and brought into contact with the first material, and then once it's heated up, it comes up and the material sticks onto the PET, so it's able to come off of the substrate. So now I perform the same process for a second material, and then it'll come together as before with, and then I'll do the same process again for a third material. So I'll do it one last time to complete the encapsulation with a fourth material, and I'll end up having a 2D stack as shown here. So this is the few layer graphene on the top, and then the twisted angle chromium bromide in the middle, and then a graphene on the bottom. So you can see that the graphene goes further wide than the chromium bromide, and this is because we want to make sure that the graphene is large enough to encapsulate the chromium bromide, so that it can so that the magnet can stay insulated from the outside environment. So twisted angle analysis. So once we have these stacks completed, then we can scan it under transmission electron microscopy. And so here's what's called Team 1 from the Molecular Foundry at the Berkeley lab. And this is the instrument used to scan the stacks. So we have a completed stack, and then we scan it under the TEM. And this TEM scan will tell us if the lattice structure of the chromium bromide layers are aligned within a few degree mismatch to call it a twisted angle. So in conclusion, so 2D magnets offer the opportunity to include magnetism into 2D heterostructures. Twisted 2D magnets can offer the opportunity to discover new phenomena, and encapsulation of these magnets allow for study outside of a controlled environment. The TEM scans will tell us the effects of twisted angle on the heterostructure, and we'll be able to compare this with TEM scans of non-twisted angle samples and compare these two. So we talked about fabrication, which is using the PET pickup method. Two-dimensional, so we know that 2D materials are materials that are less than a couple nanometers within one dimension. Twisted angle, that corresponds to the materials that have their lattice structure within a few degree mismatch. Chromium trihalides are the 2D magnets that I'm studying. Heterostructures are just the stacks of 2D materials. And then the edge alignment method is the process that I use to create these stacks. And so now this is the whole title of the presentation, and hopefully it makes more sense now. And now I open the floor for questions.
Thank you for sharing that. That's really good. Sorry, I just got here. I'm Alberto, the person you've been contacted with, and president of SPS. I should have been here earlier. Sorry about that traffic delay.
Yeah, no problem.
Yeah, do you mind if I ask questions, or does anybody else have a question before I continue? Okay, great.
I do have a question.
Mm-hmm.
So it says here, twisted 2D magnets can offer the opportunity to discover new phenomena. What kind of phenomena, can this research allow us to discover?
Right. So so essentially, because this is a new field that's being studied, so 2D magnets in itself is fairly recently being studied. So so much is still being learned about 2D magnets. So making these twisted angles will create new even more properties that we haven't seen before in these magnets. So because this happened for twisted bilayer graphene, graphene has been studied extensively ever since the creation of this field. Essentially, it's basically what sparked interest in this field, and twisted bilayer graphene showed different properties that from its non-twisted counterparts. So because of this, then there's reason to believe that the twisted 2D magnets will have a similar effect.
Very cool, thank you.
And I did want to ask a question. I don't know if you've gone over this yet, but how did you feel personally making a transition into research? And did you feel like you immediately fit in when you started with the group?
Yeah, so when I first started, I was working with an undergraduate who had almost 3 years experience in research and working with like mostly graduate students. So so I was actually very lost and very confused, and I wasn't sure if I fit in. But over time, you start to get a hang of it, and everyone's very patient with you. They don't expect you to know everything out of the bat. You just have to be willing to ask questions, and they'll be more than happy to answer your questions.
Thank you. Okay. Let me just do one. Oh, go ahead.
All right, yeah, I have a quick question. All right, so I'm not sure how relevant it is, but you showed in your animation how if you just take a twisted layer and put it on top, it does that few degree misalignment. I'm curious. So regardless of how many you stack, it seemed like there's sort of like these emergent patterns where some parts of it would essentially just be like completely matched on top of it, and then other pieces would be slightly misaligned. Yeah. I'm curious whether or not you expect for there to be different properties as you go into different parts. Yeah, sort of right there. You see how some parts, are like essentially like the same pattern in the same place, and then some are like misaligned.
Yeah.
Do you expect there to be different emerging properties out of different parts of the same material?
Yeah, that's a great question. So actually, yes. So twisted angle samples in the parts where they're aligned are expected to show like greater and stronger properties than the non-twisted parts. But in the regions where they actually overlap a lot, in like this area up here, at least for like twisted graphene, we've seen that that the properties are actually worse. So the way I like to compare it is like essentially like bringing two waves together. So if they're different waves, you'll see constructive and destructive interference. So I believe it'll be something similar to that.
Okay, thank you, everybody.
Thank you.
Yes. So if you still have questions for Carlos, I encourage you to either stay until the end of the meeting and you can chat, or maybe Carlos, if you would like to leave like a contact, I don't know if you want contact information. Yeah, so we can have some more time for our other speakers. So
yeah, I'll leave my email in the chat.
Thank you.
Thank you for everyone for listening to my presentation.
Yeah, it was really cool. I
sharing.
really like your slides and everything. They really well put together.
Thanks.
So Mina, whenever you're ready.
Okay, can you all see my screen?
Yes.
Yes.
Okay. Yeah, so hi everyone. Today I'll be talking about the project that I've been working on for the past couple months, or more than a couple months. I've been doing a project on modeling the 3D thermal emission of hot Jupiter WASP-43b, and I started this project at the beginning of last summer, doing a summer internship at NASA JPL with Dr. Tiffany Kataria as my mentor. And we weren't able to finish everything that we wanted until at the end of the summer. So it's been continuing until now, and this is something that I'm currently working on. And it's going to be the topic of my senior thesis, so this is good practice. So I'll first talk a little bit about my research path, or the different things that I've tried and how I got to do what I'm doing now. Then I'll also introduce what hot Jupiters are in general, and specifically WASP-43b and why it's interesting. And I'll also describe the models that we use for this project. And then I'll show the preliminary results of the thermal emission spectra and the thermal phase curves that I produced in the project. And I'll talk about why this is useful, and then what can be done in the future. So I first started doing research in my first year. I enrolled in this class, Astro 9 or Physics 9. If there's any first years, or I think it's also for transfer students, that if you're even interested remotely in research, I would really encourage you to take this class. It's really cool. You learn so much and you get to work on a project for 6 months. So here I worked on globular clusters as probes of the Milky Way. I discovered I didn't want to do that. So I moved on to studying TGFs of terrestrial gamma ray flashes with Professor David Smith. And here I was doing modeling of instrument response for the detectors. And then that got me interested in atmospheric dynamics and atmospheric physics. So I started working with Professor Xi Zhang in the Earth and Planetary Science Department. And here I was looking at the modeling of rock storms in Jupiter's deep atmosphere. And this project was mostly me studying about numerical methods and computational fluid dynamics and fluid dynamics. So I didn't have the chance to produce any original research here, but I still learned a lot. Oops. And then finally, last time I started this project that I'm going to talk about today. And yeah, this has been fully remote, but still I'm learning so much. And I hope that one day I get to visit JPL because I've never been there. Okay, so what are hot Jupiters? These are gas-giant exoplanets. Exoplanets are planets that are orbiting other stars or they're not in our solar system. And so these planets are really hot because they have really close-in orbits of less than 0.1 AU. And for reference, Earth is about 1 AU from the sun. They also are orbiting really fast around the star with orbital periods of less than 10 days. And for a long time, because of the short period and because they're pretty big and close to the star, these were the most abundant type of observed exoplanets. So we have a lot of data to study them. And the planet that we chose to study for this project is WASP-43b, which was discovered in 2011. And it's been extensively observed. There's a lot of data and a lot of people have tried to model this planet. So this is why we chose it, because we can validate our computations with previous studies. And then it's also interesting because it's tidally locked, which means that one side of the planet is always facing the star and the other side of the planet is always facing away from the star. And that creates a really big temperature contrast between the day side and the night side. And because of this, we expect that it's really dynamically active in reorganizing the energy. And as well, we predict that the night side will be pretty cloudy and the day side will not have any clouds. And so the two main goals of my project, first, it is to test the Picasso Python-based model for 3D thermal emission. Picasso is a radiative transfer code that is used for post-processing and computing thermal, reflected, and transmission spectrum of exoplanets. And so here on the left, you can see two figures that are taken from the Kataria et al. 2015 paper. These are models that my mentor ran a while ago. And here we can see that the day side spectra match the data pretty well. And there's very little uncertainty in the data. But in contrast, if we look at the night side of the planet, we see that previous cloud-free models don't do a good job at matching the data. It's way too bright. So it'll be interesting to see, or this was one of the main goals of the project, was to see if we can better fit the night side flux by adding clouds into the models. And the second goal, which is the one that I'm working on right now, is to develop a function that can compute thermal phase curves. And a phase curve is just the average flux of a planet, visible hemisphere, at different points in its orbit. So here you can see how it's changing at different orbital phases. This again is from the Kataria et al. 2015 paper. So we need to take several steps to model exoplanets in 3 dimensions. And the first one, we need to understand the 3D atmospheric dynamics. And we do this by using the Spark MIT GCM model. I'll talk about these models a little bit more in detail in a second. Then once we have that pressure temperature profile of the planet that arises from the dynamics, we can compute the 3D cloud profile with Virga, which is another different code. And then we can introduce these two profiles into Picasso, which will then give us emission spectra And once this project is done, hopefully it'll also give us emission phase curves. And so the MIT GCM is a global circulation model that is used by astronomers and earth scientists to simulate the 3D atmospheric dynamics of the atmosphere and the ocean. And it can be applied to hot Jupiters as well. So here on the left, there is the temperature map for WASP-43b. And you can see that you would expect the hottest point to be at the center or the part facing directly at the star, but instead it's shifted, which is telling us that the energy is being redistributed from the day side to the night side. And this is a very dynamically active planet. And then on the right side is the KZZ map, which is the mixing coefficient map. And this tells us how efficiently the atmosphere is being mixed at different longitudes and latitudes and at different pressures. Okay, so once we have the 3D atmospheric dynamics and pressure temperature profile, we can study the clouds. And to do this, we use Virga, which is an open source code based on the Ackerman and Marley 2001 model. And this code takes into account the pressure temperature profile, and it finds which species would be able to condense in different conditions at the atmosphere. And then it gives us the optical depth, scattering properties, and particle size distribution of the clouds, as well as the effect of vertical mixing and sedimentation on different cloud shapes and different locations. So on the day side, you can see that the optical depth, which is how opaque this cloud is really low. But for the night side, we can see that it's pretty optically thick. And this tells us that it is very likely that there's clouds on the night side, and these would affect the flux that we observe.
Nina,
so once we have,
for interrupting you,
yeah.
there's someone raised their hand.
Oh.
Yeah, so I think there's a question.
Is it in the chat?
Alberto, go ahead.
Yeah, it was just me. Sorry.
Okay, sorry. I can't see it.
That's okay. So when you say dynamically active, what makes the criteria for that in a planet? Or what do you look for when you give that determination?
Well, so if we go back to this figure, the reason that we know that this planet is moving, the atmosphere is moving really fast, and there's a lot going on because of this contrast between the day side and the night side. The day side's really hot, so it has a lot of energy coming into it, but the night side is really cold, so it has no energy coming into it. And then the planet tries to make a balance of that by sending all the hot air into the night side. And this creates this super fast rotating jet, which makes it very dynamically active. And all the chemistry is being redistributed. So there's a lot going on here more than, for example, in a planet that wouldn't be having this redistribution of heat.
Sorry, just real quick. So for a quick comparison, would we ourselves, Earth, be considered a dynamically active, and how would this compare?
I guess it would be different. I think all planets are dynamically active if they have an atmosphere, but it's just a different type of atmospheric circulation because Earth is rotating on its own axis. So we see very different physics going on. We still get some jets and we still get atmospheric circulation, but in the case of the hot Jupiters, they're tidally locked. So they're behaving in a different way.
Got it. Thank you.
Can I ask you a question real quick?
Yeah.
So did you say these are gas giants?
Yeah.
So so what does it mean to either have clouds or not have clouds? Because I'm thinking of gas giants as, having pretty thick, intense atmospheres. So yeah.
Yeah, that's a really good question, actually, that I had never thought about myself. I guess I'm trying to think of what would be the definition of a cloud. But I think in the atmosphere of these planets, since it's so hot, all the gases and all the chemicals are mostly in gas form. And so you need to reach certain pressure and temperature conditions for these gases to condense into cloud particles or droplets.
Yeah.
And so once you can do that, then you would have a cloud. So it's the same a water cloud. We have water in the air at all times, but you need specific conditions for these water molecules to condense and form clouds.
Sorry, I was trying to unmute. Thank you so much. That's awesome.
Yeah, thank you. Okay. Sorry, I might go over time a little bit. Yeah, okay, so once we have the 3D pressure temperature profile and the clouds, then we can put this into Picasso. And Picasso is another open source radiative transfer model. And this is used for post-processing the 3D pressure temperature profile of exoplanets. And from using this, we can make from three-dimensional data, we can make one-dimensional spectra. And it has the capability to do reflected light, thermal emission, and there's a new addition that allows it to do transmission spectra as well. So here's an example output from Picasso. Basically what it does is it takes this high resolution grid from the MIT GCM and it bends it down to a low resolution grid, and it calculates the flux at all the points in the atmosphere. And so here you can see the day side of the planet and the night side of the planet. You can see the difference in the flux here. And also, it's interesting to see that at different wavelengths, you also get different fluxes, as noted by the color bars here. So once we have the 3D thermal emission, we can integrate that flux for the visible hemisphere and get a thermal emission spectra. And so here I'm showing my current results. There are still some things that we need to figure out about this and make some adjustments. It's like figuring out whether resolution makes a big change. But I guess the main points for these figures is that for the day side, the cloud-free model provides a pretty good match to previous models and to observations. And in contrast, the cloudy day side does not provide a good match, which tells us that the day side is probably not cloudy. And then for the night side, in contrast, we see that the cloud-free model, if we look at this 1D model, it does provide a pretty good match to the previous models without clouds. But if we include clouds in the model, then we see a much better fit to the actual data, which tells us that the night side is probably cloudy. And then going to the second goal of the project, which is to compute phase curves using Picasso. We can tell a lot about phase curves. It tells us about the structure of the temperature profile. It tells us about the composition and the rotation of the planet. So here I'm showing an animation of WASP-43 rotating around the planet. So you see at different orbital phases, you see different parts of the atmosphere. And so first we need to find the visible hemisphere, then integrate the flux over angles and wavelength, and then we can obtain this phase curve that will be added to Picasso as a functionality, and we'll make a tutorial for people to be able to use this. And this is the current result. This orange curve is my current result, which is a little bit off. So there's some things that need to be fixed here, like resolution, and for example, we're not sure that we're using the right pressure temperature profile because it seems like it might be shifted a couple of degrees. So that would make a big difference in the phase curve. And those are all things that I'll be working on in the near future.
Just a real quick question about the dip in that data there at the 0.5, it looks like.
Yeah. So you're asking what that is?
Yeah.
So if we go back to this simulation here, you can see that the planet goes behind the star and then to the side of the star, but there's a point where it passes in front of the star, right? And then here we're seeing the ratio of the planetary flux to the stellar flux. So when the planet passes in front of the star, which is at orbital phase angle of around 0.5, it'll be blocking some of the light from the star. And then that is this dip over here that's telling us that some of the stellar flux is being blocked by the planet.
Got it. Okay. Thank you.
Yeah.
Okay, and not to be rude, but Mila, we can try to wrap it up in a minute or two so we can have enough time for our next speaker. Thank you.
Okay. Yeah, this is my last slide. I guess I'll just leave the conclusions up here because I think I've said all of this. But yeah, if you have any other questions, let me know. Or I'll also put my contact in the chat. But thank you. This was really nice.
Thank you. It's really awesome. There is a question. Oh, is there, Alberto, you have a question? There
Yes,
is
but
a
the other
question
one
in
can
the
go
chat, though.
first. That's fine.
Okay. So someone's, Rafael is asking, the models don't account for that. So
I'm
what,
guessing the dip.
That dip. I saw that like the observations really clearly showed that like, yeah, planets passing in front. It looked like the models from Picasso and stuff didn't really account for that. Is there like a reason for that, or did they just like not put it in?
Yeah, no, that's a good question. So Picasso only looks at the planet. So we're not looking at the planet star system. We're just looking at how this planet is. What part of the planet are we looking at every point in the orbit? But we're not accounting for the fact that there's a star in the middle that would block the planet when it's behind it, or that the planet would block when it's passing in front of it. We're just looking at the thermal emission from the planet itself.
Thank you.
And then my only question was, I know it's a bit different for for doing the work. You know, you don't really need the same skill set that you would for being in a physical lab. So instead, you'd have to know more about the programming necessary to run these simulations. Did you feel that there was a hard run into it, or did you feel like there were programs that made it easier for you to make the jump when doing research?
You mean programs as in programming languages, or?
Well, yeah. So in this case, when you're interfacing with Picasso, was it difficult to make that transition when you started?
Yes, definitely. It was pretty hard. I did have some Python experience, but I'd never been doing Python for so straight for so many hours and for so long. So for me, the biggest learning curve was learning how to use Picasso and understanding what it was actually doing. And then on top of that, I'm now working on adding onto Picasso. So I need to really understand what's in there already, what I can use to include in my code. But yeah, the programming I think, has definitely been the biggest learning curve for me in this project, but I've learned so much.
Thank you.
thank you, Nina. I definitely think we all struggle with that. So yeah, if anybody has any more questions for her, please leave them in the chat, or I don't know if you would like to leave your contact info for people to ask about. Thank you. And then we can move to Rafael's presentation. Thank you.
Hi, sorry. So I am going to apologize just right off the bat because my presentation isn't nearly as polished. I kind of misinterpreted what it was supposed to look like, so I'm just gonna do my best. Yeah, so this is my little documentation of my experience in research. I worked on the Salvation Project, otherwise known as the spectroscopic analysis of luminous variables and transients in our neighbor. And I'll get more into that in a little bit. I'm just gonna let you guys know. I'll call it Salvation for now.
Real quick, that's an amazing twisting of acronyms right there.
Yeah, don't thank me. Thank Raja. He's a genius.
Astronomers are experts in making acronyms.
They're real good at it. Yeah. Cool. So moving along. Yeah, a little introduction to myself. I talked about it a little bit earlier, but yeah, my name's Rafael. I've been at UCSC from 2017 to 2021, so I'm a fourth year. I've done some research at Lick Observatory, which is on Mount Hamilton, which is like at the edge of San Jose, the mountains. Yeah, and I've done research that's mostly focused on spectroscopy and photometry, where I look at luminous variables and transients. A lot of questions in chat. Cool. Moving along, I wanted to talk a little bit about how I got into research first. So how I got involved was like, okay, this is my schedule from 2017 to 2020-ish. Around the end of my second year, I started to get into upper division electives, and in one of my lectures, there's a professor who covered that, and he talked about his research and how like he has a and they're doing a lot of cool stuff. And what like fascinated me was not only the cool pictures he showed, but also he had a group photo that he showed where I recognized the lecturer and also a student that had been in a bunch of my classes. And that blew my mind because I was like, hey, she's an undergrad, I'm an undergrad, she's in research, that means I could be in research. So I emailed Ryan Foley afterwards, I asked about like how undergrads get into research, if he had any spots open. He let me down nice and easy because his group was full. But he let me know that like you can just look into different professors. Since we're at a research university, you can pretty much email anyone. And as long as their interests line up with yours, you're like, something's gonna happen. So it took me about a week to get up the courage because I'm a little bit shy myself. But after like a week, I emailed about 3 different professors. They all got back to me pretty quickly with like various responses, but Raja was really forward in his responses, and he was really like, we scheduled a phone call, and that kind of got the ball rolling for me as an observer on a research project. Before I get into that, I want to talk a little bit about the schedule that I'm showing. There are some repeats here. That's not a mistake. I'm just not perfect. When I went to college, I was like no calculus experience, so I messed up. Like I failed my second time taking things here. So like I barely passed 19A, didn't pass 19B. Happens. I had to retake it. I hadn't programmed at all coming into college. So first time I got programming in 119, I had to take a withdrawal. Same quarter I even got in research, which is kind of funny. But what I'm trying to get across here is like, I made mistakes, but I made up for them. And like, it's totally fine to make a few mistakes, and it's like fine to stumble along your path. Like you're probably going to be okay. UCSC is really nice. Administration super nice. What I'm trying to get across here is like, you can stumble a little bit and you'll probably be fine. Because like I ended up doing research. I'm still doing my thesis. I'm still graduating. But yeah, now that's been said, this is a lot of text. I don't expect you to read all of this. I actually don't expect you to read any of this. I just wanted to show like what was really cool to me was in 2019, like I was like, my name was on a research proposal. Like they sent this to like Observatory, and they're like, these are the people who want to do research with us. And they said an undergrad named me. And like, that was fascinating. The first time I got involved, I was the only undergrad on this project, but there's been more now. And yeah, I think it's really, it was terrifying, but also really rewarding in order like getting involved. There's this abstract here. It's a lot of words. What it boils down to is basically, okay, so yeah, sorry, all the text boils down to is like what it says here. We wanted to spectroscopically monitor and spectroscopically monitor stars that exhibit photometric variability. What does that mean? Basically, we look at these really large sky surveys, and here, I'll explain a bit more now, actually. So we use ZTF, the Zwicky Transient Facility. They have this survey. So this is the Palomar Dome over here, and they look at a huge patch of the sky. This is like the sky patch that they look at. This is LSST that's coming out soon. This is the dark energy survey. So like comparison of like what this sky looks like that we're dealing with. And all they do is that they scan the sky. They're really, really good at scanning huge portions of the sky and pumping out G and R magnitudes. Alberto, you have a question?
Yeah, just real quick about these different sizing. Does the resolution scale with it, or is it about the same?
Resolution's different for each of these. They all have their particular specifications. They even have different ratings. So the ZTF survey only does G and R band, but the dark energy survey, for example, did U, G, R, I, and Z, I believe. So yeah, these have different specifications and different things they're good at. ZTF's nice. ZTF is nice because it covers M31, which is the Andromeda Galaxy. It's our closest neighbor, which is our neighboring galaxy. That's where the name comes from. But yeah, so ZTF, they just tell you there's this point in the sky and it looks like this in G and R. They don't tell you anything else. So it's everyone else's job. There's like the University of Washington does a lot of it, and I think iSpec does some, but they basically go through those images and they assign them different tags. And those different tags and alerts and various other things just get published, and it's a lot of data. Think of like the difference between a trickling faucet and like the
Niagara Falls.
Yeah, like Niagara Falls, like how the water pumps come out, like the data is completely different nowadays. So we use this thing called an alert broker. This is why I have Antares up there. We tell Antares to look for light curves that are interesting, and interesting can basically just means not flat. We look for stars that are variable and are transient. So variable is over on the right-hand side here. This is one star that is a binary candidate for me. It's actually presently unclassified. We don't know what the star is, but we know that its red magnitude varies like this, and its green magnitude varies like this. and these are where those shots are taken. A transient is something that rises up really fast and then decays afterwards. And you can see that really, really clearly here. This is actually a NOVA candidate that another group got before we were able to. Our code told us to look here, and then before we got a chance to look here, someone else got to it. And we're like, that's a NOVA. And we're like, dang, that is a NOVA. So that's kind of cool. Do you have any questions so far? Doing good? Okay, I'm trying to go fast because I have technically 5 minutes.
No, you got overtime. Don't worry about it to compensate. Okay. Don't worry about it.
Cool. So, and what is it? Okay, so sorry, ZTF and Antares tell us where to look. Then we actually have to look there. We asked Lick Observatory to use their telescope. They have this big old cool telescope called the Shane 3 meter. It has a ton of different instruments on it. I use particularly the CAST dual channel spectrograph. Can anyone? Okay, so this is like the telescope itself is like a huge mirror with like a long arm. And you can set up this arm to reflect light in different ways. These are like the 3 main ways that the Shane 3 meter is set up to do. Anyone have any guesses as to what CAST specification is? Prime focus, Cassegrain, or I don't know how to pronounce this. Crowd. Once, twice. Yeah, I don't expect you guys to.
No idea.
Cassegrain focus. So the idea is light comes in, usually where this opening is up on here, comes down, focuses, or it comes down, bounces off a mirror down here. That's what this mirror is, and then it reflects back up. I think it hits here, maybe down here, but I'm pretty sure it's up here, and then it comes back down and it focuses on a slit down here. After it focuses on the slit, so like this is where the slit is located, down in this little tiny pinhole here. There's a slit there. I don't know if you guys have taken 5 series yet, but there's a diffraction experience that goes on here. We focus on one of those little pinholes, and then it comes down here. At C, we have a dichroic beam splitter. Basically, all this does is it recognizes where a certain angstrom split is, and it says, okay, if you are any redder than this, you get sent over to K, so down here, and if you're any bluer than this, then you get sent over to D here. And there's 2 completely different instruments on the red and blue side that register the light spectrally in different ways. It's pretty neat. There are like, I had to read all this documentation and all like the different specifications of this thing. It's crazy. It's a nuts instrument, but I like it a lot. I can spend like an hour talking about instrumentation, but I'm not going to. What it ends up coming down to is like after you do a bunch of reading, you get to use their full control room. And I was actually formally checked out. I went to the observatory and checked all this stuff out in 2019. And I was able to get formally checked out. This is a picture of my very first spectra. I love it a lot. It's such a big instrument. You have to use 3 screens in order to like use it properly. This left-hand side has the CAST motor controls. This is what controls what you're using to look at your spectra. This is what you use to control the blue side, how like long you're exposing and like what you name it. You can tell it to do multiple things here. No, actually that's here. And then this is a quick image of the spectra. You can look at it in different ways using this. Very similar on the red side with the controls, some sounds, some lamps, and then here, this is actually neat. This is an image of what the telescope is actually looking at. You can see the slit that we're using. And if you specify like a bigger slit here, you can see the slit size grow. And if you close the slit completely, you can see the slit disappear. It's like fascinating. I love it. And then here's like all the images that we can take where we send the positioning computer, which we call POCO, all this cool stuff. What it ends up going to is, yeah, so we take spectra, we like do this for, we usually start our observing nights at like 8 p.m. and then we go into like sunrise basically. Take as many spectra as possible, many different sources, like what does this even result in? What it does do is that we can produce what we call astronomers' telegrams, ATELs. This is actually one that we got to produce. One of my mentors, Monica, she produces these a lot for us. What you're seeing here is a light curve like you saw before from Antares. We're looking at this patch of sky right here. And what happened is we looked at one image here and then a second image here. And if you subtract those two images from each other, you can see a difference image. And this red circle, like you can see, something turned off there. Or actually, turned off. Let's track this one from this one. So there was light that was no longer there in the second image, so something happened. What we were able to do, but yeah, what we're able to do is point the telescope on, we actually weren't able to take the spectra for this one in particular. What we did was a target of opportunity, which is if you only have certain observing nights that you can actually observe. The other nights, if you see something interesting, but you can't observe it yourself, you can put in a target of opportunity to whoever is observing and ask them to look at it for you. So we did that. They gave us the spectra, and the spectra told us that there were pretty clear emissions here at 60, looks like 1600, so I'm guessing that's a hydrogen emission. We see some iron features over here as well. So what this told us was that this is a transient, a iron 2 type nova in M31. Nobody had known this before. This was just a spot in the sky that was just like, yeah, I guess it kind of got brighter for a second. We got to definitively say, that's a nova. And my name is on that. And I get to put that on my CV, you know, that's pretty neat. And this is just one ATEL that I've been a part of. I've been a part of at least 10 at this point. I want to say upwards of like 16, but I'm not 100% sure on that. We get to do this all the time. I call ourselves, an active team of galactic surveyors, because we're always looking at the sky and like saying, that's this thing, and that's this thing, and that's what, like, this is what governs here. The other neat thing that comes out of this is I get to, like, this is what my thesis is on. What we do is, like, these are different observation dates. So this is a light curve that I showed you guys earlier. These dotted lines are dates that we observed. So when the light curve looks like this, we can say that the spectra on those days actually effectively looks like this. And we can correlate differences in photometric variability. So this is the photometry. And then we can say, due to this photometric or correlating with this photometric variability, we see this spectroscopic variability, because the spectra varies from these different dates. Does that make sense? Cool. Going along with the spectra, this was just like a reduced, some reduced spectra. You can smooth out this spectra by comparing it to the continuum or comparing it to the error as that propagates through along as you take the spectrum. You can also define a continuum, which is just a line that links each point to each other. It kind of follows the curve of the spectrum without actually saying any of the features. So you can draw this continuum line. You can zoom in on the spectras, because like this is a long swath. It's actually kind of hard to find it's called features in this big range. So zooming in here, you can see this is what we call the calcium H and K absorption, where a calcium ion will absorb, calcium ions absorb in this little doublet here. And if you continuum normalize, so that's dividing the entire flux that you see here by this continuum line for each date, you get to normalize your flux by basically 1, and that allows you to, since like all the values basically vary about 1, you can subtract the flux and just integrate. And you can see what this feature is. We call that an equivalent width. Or you can compare the the integral of this feature. So if you just like fill this in and then compare from ground to the continuum, what would the measure like that be? And that's what you call an equivalent width. And you can see how those equivalent widths vary with different observation dates. So that's one star. I have tons of stars that I can do this with. My thesis project actually encompasses about 14 different completely unclassified stars. So yeah, where's it going with this? Yeah, I can do this with any feature along this 3,500 to 7,500 angstrom continuum, not continuum, spectrum. I'm going to basically be comparing the spectrum to different libraries. There's tons of spectral libraries out there. I think I'm specifically using the Mills library, and comparing my star spectra to their spectra and seeing how basically comparing spectra, getting ideas for different parameters like effective temperature, surface gravities, metallicities, and seeing how those factors vary as time goes on and as they're on different parts on their evolutionary track photometrically.
Can I ask a quick question?
Yeah,
The,
sure.
the list that you just gave of the different things that you can determine, are you saying that you're determining all those things from the spectra?
Effective topology and
Yeah.
yeah, you totally can.
Okay, cool.
Basically there's like a library, there's libraries and libraries of stars where we're like, we know for a fact these are at these temperatures and metallicities and surface gravities and all these things. This is what their spectrum looks like because of those factors. And if you compare your stars to those types of things, then you can get ideas for that. And then you can see how those things change and like just all kinds of steps. Those other factors also give you an idea for how, like what could be causing the variability, because different size stars and different stars and like different parts of their evolutionary tracks will be variable for different reasons. So you can even get ideas for that kind of stuff. It's very cool. I'm going to try to wrap it up. The key takeaways of what I was trying to get across in this entire thing was like, you can get started in research at any point in time. You don't have to be like a graduate student or like a fourth year. You don't have to be like where we are to do research. A lot of the people who are presenting now is like, as you saw, they got into research much earlier. You can even like I suggest being done with the 5 series in your intro requirements, but you don't have to. You can start annoying professors whenever, and something will probably come of it. The other thing I'm trying to say is like getting into research opens a lot of opportunities. I was able to be formally checked out on a telescope. I learned a ton about coding, a ton about math, a ton about stellar theory. And like in addition to those like formal experiences that I gained with telescopes and data analysis and processing, I also learned a lot from like my mentors. They told me a lot about like how to write, how to present stuff, organizational tips too. Like you learn a lot in research, and I like highly suggest it to anyone. That is all discussion, if any. I don't really have time for it, or you guys don't. So thank you guys for having me.
Thank you, that was amazing. So before we go into the questions, because I know some of you might have to leave, I'm gonna drop a bunch of information in the text in the chat box about, again, the no jargon talks that you can go and do the same thing, present about either research or a topic you're passionate about. And I'm gonna drop information about another 2 events that are not organized by SPS, a hackathon for physicists, and a documentary about diversity in physics. So if you have questions about that, you can ask me later. I'm gonna drop that, and I guess for the question, so okay, so Nina asked if Rafael has to stay overnight at Lick, but Rafael, you say that you slept over there. I've seen
Yeah, I haven't
kind
actually
of
slept
cool.
over, but I've been there twice, once for me being checked off, another for a graduate student in the group being checked off as well. You can sleep over. I just am bad about timing, so I never got to ask the Lick staff if I could. But like you can I've passed out there before, definitely.
Yeah, they have rooms for observers, also guest observers that come from other states and stuff and other cities. So you don't have to push it like that unless you're really tough.
Yeah,
that is a dangerous road up there.
It sure is.
I did have a question here, and this is, I guess, more personal to you. How did you feel after, not getting, like I like the same thing. I think it was 19A also. Like I was like, fuck, I got to take it again. So how did you feel after that about the future? In that moment, you don't necessarily feel the most optimistic.
Yeah, I didn't feel great. Like seeing like the final grade of D- on a report, I was just like, well, I guess I'm just not doing college anymore. Yeah, no, it super duper wasn't easy, but like pretty much talk to anyone who is a year or 2 ahead of you, and they're like, oh, I also failed the class. And that really helped me, just like knowing that there's other people out there who have had similar experiences and who have also like struggled for things that I find stupid or like they find stupid, like, and even if it's not actually dumb, just like complaining about things together, that really helped me continue that solidarity and struggling.
Thank you.
Oh. Any other questions, comments, concerns? Yeah, aside from that, just get into research, guys. Very fun.
I do have a question. So once you started research, and I guess this is really for anybody, like what were what did that look like? You reached out to a professor, obviously, and then, so I've done this so far, and I've been invited to some research meetings, and I'm like so stoked to be there. But I mean, every third word that they say, like, I don't know what they're talking about at all. And of course, like, I don't feel like I'm supposed to. It's a lot of technical stuff. But yeah, so, I've done that. I went to 2 meetings this week and meeting with the professor, Brian Foley, actually, again, next Monday. Yeah, I'm really excited about this. I hope I get onto the transients team. But anyway, so like, then what happened? Like, how, like, what happens? How do you know that they're like accepting you in? And then like, what do they do? Like, how do they set you up with stuff? Like, just what does that look like? What are the next steps?
Yeah, I was quite lucky because like, my next steps were I saw my name on a research proposal, and like once my name was on there, they couldn't get rid of me. So like that was my out. I don't know that everyone like gets that same treatment, but yeah, just like honestly pestering them for longer and longer amounts of time. Once they start like also suggesting things to you, I think that's a good sign that you're like definitely in it. If you like, I still don't understand plenty of things. Like I'm seeing a lot of comments like that in chat. Like, yeah, I still don't understand everything that they say. That happens. It's just going to continue happening. Honestly, what I do, I have like a little writing pad that I write stuff down on. Any words that I don't get and that I want to get, I just like look up afterwards. There's a lot of good documentation, and a lot of the mentors and stuff, they are 100% willing to like give you some reading on stuff that you want to know more about or don't know about. And if they have the time at that point, like if you hear the word and you're like, oh, I don't know what ZTF is, you could ask possibly like right then and there, and be like, oh, it's a transient facility, and like then you'll just know. Yeah, like asking questions, like being nervous about asking questions is certainly hard. I deal with imposter syndrome myself pretty heavily, so it's hard. Don't get me wrong, but it's just something that like over time gets easier, I think. I don't know if anyone else has a similar experience.
Oh yeah, man. I'm in my meetings now and I'm like, I don't know what that one word is. And then they're like, oh yeah, I learned this while doing my PhD thesis. I'm like, well then no wonder I don't know what that is.
Like, okay, Mr. Expert.
Yeah, I'm like, all right, I'm very proud that you've got your PhD. Oh God.
But, I could recommend just asking questions. Most of these teams have a lot of postdocs and grads as well. And usually undergrads get to work with them. And so they are happy to answer questions. I mean, that's part of their process too. So don't take that away from them. Many of them, if they don't place in research, will place in academia. So it's great training for them to work with undergraduates and others and inform them properly. So don't take that chance for them to learn away as well. Just ask your questions, and it'll be a great dynamic.
I think for me, I would recommend reading a lot of papers. I found that it was really hard for me to read papers at first because I had no idea what they were talking about. And I mean, I've been in several different groups, so I feel like I've never stayed long enough to really feel like I am a part of it fully. But in this last project, at first I was so lost, like I'd never done anything like this. And thankfully my mentor was really supportive, and just realizing that other people make mistakes too, because it's really easy to feel like you're, I don't know, messing up and not good enough. I've definitely felt like that a lot, but I mean, everyone makes mistakes and it's a long process. I think my mentor was saying the other day that it's not like classes. You can't, there's like no recipe to do things. So you kind of have to figure it out. So, I mean, just patience, I guess.
Thank you, everybody, and thank you for like all the comments in the chat and for all your experiences. This is really important. I'm super proud of seeing your research, your presentations, because I've seen Rafael, I've seen you in class, but we never really talked. And Nina, we've talked a little bit, but I never really asked what you guys do. And same thing with Carlos, but he left. And it's just really cool to see where you guys are. Wait, how far you come? Like, you're like, well, I'm supposed to be there too. But yeah, thank you. And I hope this serves as inspiration for everybody else. We're gonna be there someday. So I hope you have a really good rest of your day. We're gonna end the meeting here. Sorry for going over. We hope to see you next week. We're gonna have a game night. We're gonna be playing Among Us. Just one last try before finals. And good luck with the rest of the quarter, everybody. And thank you.
Thank you, everyone.
Thank you so much.
Thank you.
Everyone, stay well.
Bye.
Thank you. Great job, speaker.
Everyone, yeah, thank
Yeah.
you. Those were awesome presentations.
That was great. Take care.
Nice night, guys.
Bye.
Are you gonna
Okay.
stop recording?
Yeah, I'll stop recording. No, I'm not recording.